And she's going to talk about geometric relations of bipartite graphs, totally non-negative Grassmannians, and application.
Okay, thank you, Marco. So first of all, it's a great pleasure and honor to have been invited to this workshop dedicated to John Harnad, which I met the first time, I think, in MSRI during the program of 1999 on random matrix models and integrable systems. And since then, we have met around the world many, many times. I'm really sorry of not being there in person, but unfortunately, this is the period of the year in which I have a lot of didactic activity. And so it was really a nightmare to organize a trip because I couldn't really manage to do it. So I hope next time you organize a workshop, it will be during the spring semester or in summer when I'm a little bit more free, and it will be a pleasure for me to come again to Montreal. It's a place which I always come to with a lot of pleasure, to see old friends and also to have new friends. Okay, so in this talk, I will talk about some work which we did with Piotr Griniewicz in the past few years concerning the construction of spectral data for KP real regular final gap solutions, which are connected to totally non-negative Grassmannians, and basically using a lot of combinatorial results or related to totally non-negative Grassmannians. And if you restrict the class of Postnikov graphs to the bipartite case, there is also a nice relation to the dimer model, which was immediately understood by Postnikov himself and Speyer and Williams in an old paper of them, and which basically provides a version of a Castellane theorem and a different interpretation of a boundary measurement map, of a Postnikov boundary measurement map, which is useful in our construction. And this connection between, let's say, Postnikov boundary measurement map and bipartite networks, and dimer model, goes through on bipartite networks in the disk. If you go to the more general class of graphs considered by Postnikov, the Postnikov boundary measurement map is equivalent to a different mechanical statistical model, and of that we have an example in one of the papers with Piotr. So, okay. So I will start recalling what are totally non-negative Grassmannians, positroid cells, and essentially the type of graphs we're using. So we can think of the totally non-negative Grassmannians simply as equivalent classes of full rank K times N matrices whose minors are non-negative. Of course, modulo the linear recombinations of the rows. To each such point in the totally non-negative Grassmannian, there is a natural matroid associated, which is formed by the set of k-column indices corresponding to the minors which are positive. And one can define positroid cells as the point in these Grassmannians in which the maximal minors, which I denote delta I of A, are positive, and that occurs if I is a k-element subset in the matroid, and of course in all other k-element sets, the minors will be 0. Of course, positroid cells, there are certain conditions for which, of course, not every combination of positive minors is, of course, possible. And so this can be thought of as intersection of the Gelfand-Serganova stratification with the total positivity condition. For what concerns us, each positroid cell corresponds to a family of real regular multi-line KP2 soliton solutions. And these solutions were, the asymptotic behavior of these solutions was thoroughly studied by Kodama and his collaborators. I just want to mention Gino Biondini, Chakravarti, and Lorraine Williams in a series of really important papers. And for what concerns Postnikov classification, each positroid cell is represented by an equivalent class of bipartite graphs in the disk, which were classified by Postnikov in his seminal paper of 2006. The problem we were interested in with Piotr is connected to real regular KP finite gap solution. So what we constructed is a recipe to obtain spectral data for real regular finite gap KP2 solution by solving a degenerate spectral problem associated to this family of real regular multi-line KP solitons. So here on the top left, I show a picture of a KP solution in the space-time, xy for fixed time. This is actually a periodic solution, real periodic solution, but in general you expect a quasi-periodic solution. So by Khrushchev theorem, we know that these family of solutions are associated to an algebraic curve of genus G, on which you fix a point P naught, which is basically gives you the essential singularity of a KP wave function, and the position, and then you have a divisor in general position, in this case is P1 and P2, which rules as basically the solution you are considering. And in the case you are interested in solutions which are regular for real KP times, then in a theorem by Dubrovin and Natterson of 1988, it was specified that your curve must possess an anti-holomorphic involution, which fixes the maximal number of ovals, which for a genus G case is G plus 1. And the position of a divisor point and the infinite point is that they are obliged to be in these ovals. So the oval to which the essential singularity of the wave function belongs to, P naught, belongs to one ovals, which is called infinite, and all other ovals are called finite, and there is one divisor point in each finite oval. So for the solution shown to the left, and on the right, there is it corresponds to a genus 2 solution, so an hyperelliptic curve, and I show the ovals in green, and the divisor points are P1, P2, and the P naught is this one. Okay, of course, one can degenerate this solution, and in the solitonic limit obtain when some of these cycles degenerate to double points, one obtain other kinds of solution. In particular, in this case, if you pinch to double points, you will get soliton, multi-soliton solutions. The real regular multi-line KP soliton solutions corresponds basically to points in the totally non-negative Grassmannian. And the idea which we had with Piotr was to use the generalization of Khrushchev theory of finite gap for finite gap solutions, and reconstruct, associate to these multi-line solutions a curve which consists of several copies of rational curves which are glued together at double points in such a way that we form G+1 ovals, the real part of the curve, and to use basically a system of relations on the corresponding dual graph, by which we construct the wave function, the KP wave function at the double points. And the total non-negative property is essentially what you need to ensure that in this construction you may respect Dubrovin-Nathanson theorem. So the divisor points for this solution will be in the finite ovals, and therefore if you desingularize the curve opening the gaps, then you will obtain a curve and a divisor as predicted by the theorem of Dubrovin-Nathanson. Okay, so how we do it? Let us summarize. So every multi-line Solton solution is represented by a point in the totally non-negative Grassmannian. We use this whichever extension of finite gap theory to the case of reducible curves. And to construct the curve, we choose a plabic, so a planar bicolored graph, representing the point in the Grassmannian in the classification of Postnikov. And this graph is the dual to the general spectral curve with the usual correspondence. Ideas, the vertices are copies of CP1, the edges correspond to double points, the faces are the ovals, and moreover, the graphs of Postnikov are inside a disk. So for us, also the boundary of the disk is another copy of CP1, and it has a special meaning because it is exactly this only copy, the one which you can see from the direct problem. So of course, if you have multi-line Solton solution, you have associated to it a rational curve and a point which is the essential singularity, and a finite number of divisor points. Okay, and so this is the data which you directly reconstruct. But of course, these data are insufficient in general to obtain in the inverse problem your Solton data, because there is not a good, the dimension of Solton data is bigger than the divisor you can construct this way. So this construction is necessary in order to be able to perform the inverse problem in finite gap theory. So, as I told, we use a system of relation of the graph to compute the wave function at the double points and to assign a divisor point to each finite oval. And to perform this task, we generalized a formula of Talaska for Postnikov boundary measurement map. And the total non-negativity property is what ensures that the regularity and reality condition of the theorem of Dubrovin-Nathanson are fulfilled. And basically, if you choose your graph to be bipartite, then it is a Castellan type theorem which rules the system of relation. And moreover, our construction may be interpreted as amalgamation of little positive Grassmannians, where, of course, which are, of course, the GR plus 1 free and GR plus 2 free, which are represented respectively by trivalent white vertices and trivalent black vertices. And in our construction, to each trivalent vertex, we associate a copy of basically the real projective line, in which at the edges, which are the double points, we assign with our construction the value of a wave function, and then we extend it meromorphically to the cool CP1 copy, and we get one divisor point. Of course, if you singularize and the divisor point is in general position, you'll be also in general position on the desingularization. And instead, for the black boundary vertices, we prove that in our system of relation, the value of the wave function at the free double points is equal So we just extend for the solitonic case to a constant function and then desingularize it. You will not have any divisor point on it. Okay, so here is an example of how we construct a rational degeneration of M curve. So on the left, I show the topological representation of this degenerate curve, reducible curve, which is formed by several copies of CP1, which are represented by these lines. And here, basically, of course, you obtain this topological model by partial normalization. And you can identify, if you look carefully at the picture, the finite ovals on the left with the finite ovals in the central of the center figure. And on the right, I'll show a desingularization. So this is something which can be done explicitly, let's say, in algebraic terms. And so this is, we have, of course, explicit representations for these curves at the end. Of course, after we have a curve, we need to assign the value of the wave function to the double points, which are these points here, in order to have a consistent construction of the wave function of this reducible curve. And here, if we work in the bipartite case, is where the diamond models come in and its relation to Postnikov boundary measurement map. So I will try to explain this mechanical statistical construction. So a dimer configuration for a bipartite graph in the disk, or also called an almost perfect matching, consists of a collection of edges in the graph which contains exactly once internal vertices and at most once the boundary vertices. And then you can define the boundary of your configuration as the set of the black boundary vertices which are belong to the dimer configuration and the set of the white boundary vertices which do not belong. So in order to make simpler the relation to Postnikov boundary measurement map, it is convenient to work with black boundary vertices, so have all vertices of equal color. And in this way, it is clear that the boundary vertices which can be occupied corresponds to k element subsets in your in the matrix which I was defining before. And that is because essentially you may reconstruct the matroid of your positroid cells through the perfect orientations which are admissible for your graph. And these perfect orientations are in bijective correspondence with the dimer configurations which you can have. And this is a theorem in Postnikov, Speyer, and Williams. I mean, it's part of this paper of 2009. And it is the bijection which I will use here is the following one. You consider the site occupied if your perfectly oriented graph, the edge is oriented from the black to the white vertex, and free if it is oriented from white to black. And in this way, one can reconstruct, I mean, associate dimer configurations to perfect orientations. So, what is a Postnikov boundary measurement map? It comes from discrete integration over your directed network. So, in your directed network representing a positroid cell, you have a set of vertices which are the sources from which you, in this figure here, are B1, B2, B4, and B7, and the remaining boundary vertices are sinks, so arrival points. of the possible words. So in this case, B3, B5, B6, B8, and B9. And then to construct a representative matrix of your point, in the Grassmannian, you consider all walks which start from the same boundary source, let's say B1, and arrive to the same boundary sink, let's say B9. And then you associate to each such walk two numbers. Its weight, which is just the product of the edge weight, and a topological winding, which is thus the number of complete counterclockwise, complete turns of 360 degrees, which you do in your travel from the source to the sink, which are counted positive if they are anti-clockwise and negative if they are clockwise. And finally, you have also a term here. Another, the sign is completed by counting also the number of sources between I, R, and J. So for the example under consideration, if you consider the walks from B1 to B9, you can go in some different ways. You have three different ways to reach the boundary 6 B9. The winding in all of the three cases is 0. And the number of sources is 1, 2, and 3. So here there will be a minus sign in the entry. There is also a different way to reconstruct the point in the Grassmannian, which was pointed out by Thomas Lamb. If you consider the dimer configurations, you can associate to each dimer configuration a weight, which is thus the product of the edge weight belonging to the dimer configuration M, and a partition function, which is the sum over all configuration which shares the same boundary of these weights. And these are just the Plucker coordinate or the same point in the Grassmannian which we're obtaining with a Postnikov boundary measurement map. Okay, so so the questions arises if you have a concrete way to compute, an efficient way to compute this point, and a possibility comes using the theorem of Castellane. So the classical theorem of Castellane tells you how to count dimer configurations in planar graphs as determinants, if you are in a bipartite case, as the determinant of a square matrix in which the rows are the white vertices and the columns the black vertices, and the entries is either +1 or -1 when there is an edge joining the black vertex B to the white vertex W, and is 0 otherwise. Spire in 2016 topologically proved that it was possible to associate to each network of Postnikov and bipartite a Castellane matrix in which you assign plus or minus the edge weight if there is an edge between the black and the white vertex, and 0 otherwise. And the absolute value of the determinants of the maximal minus of this matrix are the Plucker coordinates of the same point which you obtain in Postnikov parametrization of a totally non-negative Grassmannian. And there is also a way to construct the matrix, just transforming your Castellane matrix, which is full rank, into block form. And so with southeast blocks form, you read out your matrix. Okay, so a question is how to assign these signs. Okay, with Piotr, we found the answer through geometric indices, and this can be translates in the case of a bipartite graphs into assigning a function to the edges which will be a Castellan signature in the sense of spire, if and only if for any finite phase omega of your graph, the total signature equals half the number of the edges plus 1. So this is exactly the usual Castellan condition in this case, where, of course, the infinite phase of the graph is the one containing, in this case, is the phase containing the part of the of your boundary of your disk, which is oriented clockwise from the highest boundary vertex to the smallest boundary vertex. So that is the infinite phase. So here I show an example for this graph of a Castellan signature. And if you are in the disk, there is a unique Castellan signature of a graph up to vertex gauge equivalence. Okay, so of course, since we have a matrix, we have also a system of relation which we can build on it. And this is done assigning an element of some vector space to each black vertex and the equation, the system of equation, which comes by applying the Castellan matrices to the this set of elements VB, and just solving this linear system of relations. So what I proved is that if you choose V equal Rn and you take as at the boundary sinks the canonical vectors of the base in Rn, then at the boundary sources you reconstruct Postnikov boundary measurement map up to the pivot term. And in the case of a spectral problem for the KP2 equation, if we assign to the black vertices the value of the KP wave function at the time x, then if you solve this, the solution to the system will give the value of the KP wave function at the double points on the reducible curve. And that means, of course, that you need a formula to find the solution. And this is what we did with Piotr, generalizing Talaska formula and assigning a geometric signature to the graph. Okay, so our idea was to use discrete path integration, and we used a gauge ray direction to measure the winding, locally the winding between consecutive edges, and assigning an intersection index to each edge. Indeed, if you remember, in the formula by Postnikov, we have a winding number, and we have somehow to count the sources between the starting point and the ending point of your path. But clearly, if you start inside the graph, there is not a well-defined way to say how many sources you have between your edge and the ending point. So to overcome this problem, we introduced this index, the second index, and it did work. So, of course, the system of relations, which I showed in the previous transparency, can be transformed in a system of relation on the edges of a graph, which is a more convenient approach if you want to generalize a Postnikov formula. And so in this case, the edge component, the jth edge component of your edge vector on your oriented graph will be the sum over all walks from the starting edge to the sink of this number, which associated to the path, which is just the weight of the path. So the product of the weights of the edges which belong to your walk, the intersection index of a path, which will be just the sum over all edges of the intersection number, And the winding of the path will be just the sum of these local windings between consecutive edges.
Simonetta, I have a question. So if I understand, can you also phrase it this way, that you are cutting your graph along these directions and then thinking of the intersection as sources and sinks?
Yeah, okay. The idea, what we do is you choose a gauge ray direction. This gauge ray direction, when you take gauge rays starting at the boundary sources. Okay, so in this case, you are in GR to 5 and GR plus to 5, and here we choose as sources B2, B3 and B5, so GR to 6, and so here are the two rays, and here, for instance, the intersection of this edge is 1, the intersection of this edge is -1, etc. And the winding is just, you look at the two consecutive edges and check if the gauge rays is between the two consecutive edges. And then you assign winding either +1 or -1, depending on the ordering of the three. And otherwise, this winding is 0. So, for instance, in the example, you consider the winding number associated to the edges E32 and E20, that will be -1, because if you look at them, you have basically the opposite orientation. So this is E32, here is E20, and in the middle you have a gauge ray direction. And okay, so this is the way. Instead, if you look at E01 and E12, the winding is 0, because the winding is the gauge ray direction is outside this the interesting interval. So we have a well-defined way to construct the winding, and actually this winding was introduced by Gechtman, Shapiro, and Weinstein in a paper of them, and we applied it to construct these edge vectors, adding this intersection number. And what is interesting is that what we got is a generalization of the formula by Talaska. So Talaska explained how to compute Postnikov boundary measurement map in terms of flows on your graph, directed flows on the graph. And in our formula, we generalize that formula, so we solve a linear system of relations at the internal vertices, or you prefer at the edges of the graph. And the edge components we show are rational in the edge weights with subtraction-free denominator. So the denominator, here you see the sum of the weights of the closed simple cycles, which you have in your directed graph. And in the numerator, you have the winding of the flow. And the flow is formed by a non-intersecting path, a simple path from the edge to the boundary sink, and collections of closed cycles, which have to be, of course, must not have vertices in common. So here the formal definition is in our paper. It is just an adaptation to this case of a formal definition given by Talaska. And if you consider the edges at the boundary sources, you obtain Postnikov boundary measurement matrix. And exactly Talaska formula. And we have a complete control of what happens to these vectors when you change the gauge direction, the orientation, and the weight gauge. So you show that these are just correspond to gauge transformations. Basically, to a change, if you prefer, just a change of basis in your system. So locally, of course, inside the solution will depend on the gauge which you choose, but you can find a normalization which will make them independent. And that is the reason why it works with the KP wave function. So you have up to after you normalize the wave function, you basically eliminate this gauge freedom inside, and so you have a well-defined wave function at the double points, which corresponds exactly to the edges. And of course, what I said suggests that there is an invariant way to perform this computation through the introduction of a geometric signature, which has this ugly definition here. I show, so you have 4 possibilities in a bipartite case, which is black, white, white, black, and black source to white, or white vertex to black sink. Of course, if you are not in a bipartite case, there are other 2, white to white and black to black, which is in our paper with Piotr. And what we prove with Piotr is that on the graph, there is a unique geometric signature up to vertex gauge equivalence. So a natural question is, what is the relation between the Castellan signature and the geometric signature? Since in both cases we get the same map as Postnikov, they have to be related, and indeed this is the case for bipartite graphs, where Castellan is meaningful, I mean, as a mechanical statistical model corresponding to the Postnikov map. Indeed, with Piotr, what we proved is that if you compute the total geometric signature of your face, this depends only on the number of white vertices bounding your face. So if you are in a finite face, it will be just the number of white vertices plus 1. If you are in the infinite face, it will be the number of white vertices plus k. If you are in GRK n, okay, is the Grassmannian corresponding to your graph. And of course, if you are in the bipartite case and the boundary vertices are black, and it's just a 2-minute computation to understand that your signature is Castellan, even only if your corresponding geometric signature satisfies the requirements of our paper with Piotr. So it is just the same things, only constructed in a different way. Okay, so here I show how you assign to the graph, which I showed before, with that orientation, the geometric signature, and one can check that it fulfills both the theorem of Castellan and our theorem with Piotr. And therefore, what we use, it's the generalized Tasker formula to compute the wave function at the double points and Castellan relations at the white trivalent vertices give a position of a KP divisor in the ovals. And the fact that we are in a totally non-negative Grassmannian, so Castellan theorem holds, if you prefer, implies that we will get one divisor point in each finite oval. So there are many open problems to what we did with Piotr. First of all, we don't know which are the M-curves which are associated to this Postnikov plabic graph. What we know is that if you work with soliton data in GR+1n, what you get are hyperelliptic genus n-1 curves. And we constructed an example in GR+4, and we showed that the curve we obtain is trigonal genus 4. But for the general case, essentially, we don't know what kind of curves we can obtain in this way after the singularization. Another interesting open question is which varieties in the positroid cell correspond to the reductions, important reduction of the KP hierarchy, like the KDV, the bussiness, etc. And of course, we are working with a degenerate Jacobian. So basically, what we have is that depending on the position of a divisor, before we singularize the curve, we get different families of soliton solutions. What it means from the point of view of graph theory, it means that you have to classify which color changes of the vertices in a graph are admissible. So send your perfectly orientable graph into another perfectly orientable graph. So this is a map between different positroid cells, because it is a map between different families of solitone solution. And another thing which is, I think, extremely important would be to understand the connection of our construction with the approach of Kodama and Williams. So basically, to study the asymptotic behavior of the zero divisor in order to check if we have to, what we know is that what is clear is that we have to obtain exactly what Kodama and Williams obtained, but in a different way. So it would be nice to check that we can reobtain the same results that they got for the tropicalization of these solitone solutions. Now, if I have still some minutes left, I would just tell some words on some recent work of mine, which I will put on archive in a few weeks. I'm just finishing writing it, and concerns the, let's say, generalization of the Talaska formula when we work with dimer models on surface graphs with boundaries and its connection to a generalization of a boundary measurement map. Okay, this problem was already considered by Geften, Shapiro, and Weinstein, who generalized Postnikov boundary measurement map to the directed graphs in the annulus, and also by Machachek, who, let's say, studied the case, same problem on orientable surfaces with boundaries. The boundary measurement map constructed in these papers depends both on the perfect orientation of the graph and on the cuts between different boundary components. There are many generalizations also of the Castellan theorem and the dimer models. And in particular, in a paper by Cimazoni and Reshetikin, they basically characterize the partition function for the dimer model on surface graphs with boundary through linear combination of Pfaffians of Castellan adjacency matrices associated to the different equivalent classes of Castellan orientation. So basically, the dimer models is exactly the same also of the surface graph. So you use all internal vertices and some boundary vertices. And the dimer partition function is for a certain boundary is just the sum of the edge weights of the dimer configuration. And this is the formula by Cimazoni and Reshetikin, which depends on the genus of the surface and the alpha invariant associated to a convenient quadratic form, a number which comes from the Castellan equivalence class of orientation, and of course the Pfaffian. And so what I was interested in was to understand this was, a relation between these two approaches, which is not so obvious from what I said up to now. Okay, so how I define the Castellan signature. So for simplicity, I'll show an example on the annulus just to make things simpler. Okay, so the first, my idea was to use a Castellan signature. And the question is how to define a Castellan signature, for instance, in an annulus. So in the disk, we have an infinite face, and it's, on which everybody agrees. And my idea is to use, to associate to each boundary component an infinite face. So in the annulus here with two boundary components, you have two infinite faces. And to fix the Castellan signature with the usual condition on the finite faces. For this example, what one can prove is that there are 4 equivalent classes of such signatures. And if you work with a definition of Cimassoni and Reshetikhin, you get two equivalence classes of Castellan orientations. So with the number of Castellan orientations grows with the genus and the number of boundary components, and the same is, of course, for Castellan signatures, but here for Castellan signatures, the way they grow is much faster in a sense. Okay. And then you associate the Castellan sign matrix exactly in the same way as was done before. And what you get is a natural map to the Grassmannian by considering the maximal minors of the Castellan matrices formed by all the, using all the white rows and the columns and adding the columns which correspond in the black vertices to your boundary of the configuration. Of course, to each, what is clear is that to each equivalent class of Castellan signature, in this way you associate what you can call a Castellan boundary measurement map, which with values now in the Grassmannian. If the weights are real, will be the real Grassmannian. If the weights are complex, the complex Grassmannian. Where the K is the basically is viewed by the cardinality of the boundary of the configuration, and N is the number of the boundary vertices. Of course, if you work with real weights, the variety in the Grassmannian which are describing is independent of the signature, because here it's just a plus or minus, so it's just a transformation of the weights. Of course, if in your application you are interested in real positive weights, what you describe are different objects. And what is interesting is that if you are working with in the annulus with a finite number of boundary components, then for any given boundary condition, you may find a Castellan signature whose corresponding minors just gives you the partition function for that boundary condition. So, okay. The question is now how to efficiently, how can you use the Alaska flows to compute these maximal minors in general. Okay, the boundary measurement matrix now is defined as the ratio of two of its minors when you are just changing one entry. And of course, here the sign is again the number of elements in the boundary condition, DM0, which you can think of as the source set of sources in the interval between the given source and the same. So this is essentially the same we had before. Now you define an undirected flow as the union of a two-dimer configuration to which you eliminate the edges which appear twice. And this is clearly something which will be, in general, a path from a boundary source to a sink and a bunch of simple cycles. And this flow you call clockwise odd if it respects a Castellan condition, otherwise you call it clockwise even. And what you get is the following formula, which generalizes to surface graphs with boundaries, the Alaska formula, and coincides with the usual Alaska formula when you are considering bipartite graphs in the disk. And it's just a combinatorial. So I finished, and I want just, sorry, everything is blocked. Thank John again. And here I found a picture on one of the many workshops I participated in Montreal. So it's not, I don't know if it's visible, but here is John, here's Marco, and here it's me. Many other people from which are present in the workshop. couldn't find one in which all the people participating in the workshop are present, but okay, that's the best I could do. So thank you very much for your attention.
Thank you, Simonetta. I think you can zoom in, so probably we can see better.
But the picture is not a very high quality, unfortunately.
I think, okay, but there's Misha.
This is, I mean, this is not my fault. This is the site of CRM. So,
okay. Thank you, Simonetta.
That was the best I could do. So, but you can recognize yourself, I think.
Yes. John, Misha, and you.
Yes, Misha is there. So. Yeah. It's this is Canyon, and probably there are many other people.
In which year was that?
Sasha Orlov, I think, is there.
I think 2015, maybe, because here is Lauren Williams. I think it was the workshop.
Positive Grassmannians, yeah.
Yeah, positive Grassmannians, yes, where I first presented the first paper with Piotr. So it's also it was in Montreal, so it has a particular importance for me.
Thank you, Gabe. Are there questions for Simonetta? Comments from online?
We can't leave it without the question.
I have a question, but I leave others first. So, Simonetta, in your conclusions, at some point you mentioned that you want to classify the paths. I forgot now. Can you roll back to the I think it was 16 or 17.
Okay, sorry, I make it smaller because otherwise we don't see.
So
and maybe
slide 17, 16, something like that. When you had your conclusions, open problems. Sorry.
Open problems. Okay. So here it is. Yes.
Yeah. So so you say classify color changes, etc.
Yeah.
So
because your curve is independent of the curve is the same independent of the color changes. What changes in once you assign the color? I mean, remember the black vertices are those which correspond to the parts in which you don't construct divisor points, so the trivial points. Okay. And the white vertices where you have your relation, and your relation, assume everything is trivial for simplicity, will give you one divisor point. Okay. And the construction is done in such a way that you get exactly the expected number of divisor points, which is if you have G plus 1 faces, including the infinite face, you have G divisor points. So the question is how you can change the color of a graph in the graph vertices in such a way that you still obtain a graph in Postnikov classification. Now, of course, changing the colors will switch you from one positroid cell to another positroid cell. Right. So to a family of certain solution to a different family of KP certain solutions.
But,
so they correspond to the same, let's say, when you open the gaps, they correspond to the same real regular final gap solution. So your Jacobian is degenerating in several components, let's say. And what, so it's somehow to, basically it gives you a sort of...
I thought that there was wasn't there a procedure by which you choose a path from a sink to a source and then you switch?
No, but this is clear. If you fix this is to basically get a transformation from one family of solution to another family of solution, okay, which correspond to algebraic data on the same curve. This is the problem. So I know what to do if I fix the family of solution. It's no problem. I fix the. I know which family of curve I have to use. Mm-hmm. Okay, and how to do the construction, and it works. But once I have the curve, I want to mix things and change the colors. If you change the colors, it means that you change the number of white vertices. So you pass from GRKN to GRK prime. Okay. Mm-hmm. And the number of boundaries vertices is the same. So you change from K to K prime. or maybe in the same K, but different positroid cells. So many things may happen. And but in general, you change K. And so it is unclear. So consider that the graph can be reducible in Postnikov sense. So it would mean that you are not describing your Solton solution in the lowest dimensional positroid cells it belongs to. Okay, a Solton solution belongs to an infinite number of positroid cells. What is well defined is the minimal dimension of a positroid cell in which you can see it. This is a problem in graph theory, but it is connected to a question to, I mean, it's a problem of understanding the structure of these curves, basically.
Okay, thanks. But it's really beautiful pictures, geometric picture. John, I think, you have a question?
Yeah, so let somebody else. Don't want to be boring. Simonetta, lovely talk. I can only pretend to have understood some part of it, but the stuff about the generation of quasi-periodic solutions to solitons, I think, is the part that I understand the best. But there was something just technical, which you said when you were talking about these various plabic graphs.
Mm-hmm.
We're talking about gauge fixing or gauge rays or something like that.
Okay.
Is that right?
We have, okay, when in the construction, which we do with Piotr, we have a lot of gauge freedom because we choose a gauge ray direction. We choose an orientation in the graph. We choose a gauge direction and we assign the weights on the edges. So of course, there is a gauge equivalence class of weights. If you change the orientation of the graph, the boundary measurement map is invariant. And if you change the gauge ray direction, we also show that the boundary measurement map is invariant. I mean, our map is invariant because we get the same solution. So here, of course, at the internal vertices, you see this local transformation of the vectors. So from the original, if you change the gauge direction, the only thing at the internal vertex is either your edge vector remains the same or changes of sign. If you change of orientation, the new edge vectors will be a linear combination which contains the previous one and a linear combination of the rows of the boundary measurement matrix. And if you change the weight locally, you see that your edge vectors will be transformed by a constant which is different from 0. What I'm saying that this is not a problem in the construction of a KP wave function, because what you work with is the normalized KP wave function when you construct the divisor. So this is Krichever. You use a different normalization. So when we do this construction, we use a normalization of a KP wave function which is not Krichever. And if we pass to Krichever normalization function, we get something which is invariant. And essentially, in this, we gauge out all these freedoms and we get a unique solution. So what you show is that if you pass to the Krichever normalization, you wash out all these gauge freedoms, basically. And so at each double point, there is a unique, from your construction, our construction, there is a unique value of a normalized KP wave function. Okay, so the construction is well defined. But in order to get this, we had to use this other normalization because it made things simpler. So I mean, you needed to get the solution of the system is not the solution to the system as we write it in the directed network is not Krichever. Okay, is a different normalization of the wave function. But so it's after you pass to the normalized wave function, you get exactly the correct one. So if you prefer, the position of the KP divisor doesn't change. It's just that you look in different local coordinates. Okay, That depends on how you orient the graph. Because of course, when you we assign a local coordinate to the double points, which are the edges in the graph, and so this correspondence. Of course, if you do not normalize, you see the local coordinate, so it seems that it changes, but it just you see that you can prove it. This is just due to the fact that you're choosing certain local coordinate instead of another one. But the position is that is there in the is invariant in the oval. Okay. I don't know if I answer your question.
No. I mean, thank you for all that information, but my question was a much more primitive one. I understand. Okay. I'm trying to understand in what sense your gauge transformations are equivalences. Now, wait, don't answer until I ask the question. Your gauge equivalences really are somehow equivalences. I know in the context of Grassmannians, I mean, infinite Grassmannians, and KP solutions, I know what is usually called gauge equivalence. It's a change, well, at the level of the wave function is just multiplication yes. by gamma minus element. I mean, a negative exponential of a negative power series in the spectral parameter. And that does, because you're taking logarithmic derivatives, that does not change the actual solutions.
Okay.
Equivalently, the level of the tau.
So you were asking what is this?
Just a second, Simonetta.
Wait, so it's okay. The gauge
is your notion of gauge transformation that one, or is it another notion of gauge equivalence?
No, these gauge equivalence, which I'm talking about, are connected to our construction and to the properties of a Postnikov classification. So the gauge freedom in the weights is the fact that you have the same network if you change the weights at the edges by multiplying by a positive number if at the starting vertex and divided by a positive number at the ending vertex of your. So this is the kind of gauge equivalence of weights in a Postnikov sense and the usual sense in graph theory. Clearly, in our construction, we are fixing an orientation. So you have another gauge freedom, which comes from changing the orientation of a graph. Changing of the orientation of a graph doesn't change the solution, doesn't change the divisor. Okay? So these are, and changing the gauge redirection doesn't, again, change the construction of the wave function and the divisor. So these are the kind, and these are gauge freedoms associated to the graph and the network we are using. Okay, so it's not the gauge freedom you're talking about, I think.
Okay, but for each one of these graphs, you have some kind of KP solution, right?
Yes.
And I mean, so when you make the gauge transformation,
each graph is associated to a family of KP solution. If you take edge weights in the same equivalence class, you are describing a unique KP solution, multi-line KP solution. Okay, and
so it doesn't. It really does not change. It changes the tau function, I suppose, but it doesn't change the solution.
Yes. Indeed, what I said is that the KP wave function, if you use the Krishever normalization, which you put the divisor in the denominator, it fixes the divisor. So you fix that normalization, all these freedom will be washed out. Okay, all these gauge freedoms which I described will be washed out. Yeah. Yes, so you are really describing a unique solution.
It's identically the same. Okay, Marco here is saying it's exactly the same tau function. The gauge transformation I'm talking about multiplies the tau function by a linear exponential factor in t's. And so it's
but this is what you have Okay, but this is just when you look at the time evolution of your solution, you mean?
Sorry, Simonetta. I also have another question.
What we do is exactly the time is is considered in our solution. So here. Yeah.
Yeah. Sorry.
His axes are the time. So the fact is that here you have. I mean, what you know are the value of basically the construction works because the value of a wave function at these market points K1, K2, K3, K4, K5, K6 is fixed by your Soliton solution. So this, you know, if you give me a matrix, I can tell you which are these values of these points. What we prove is that if you assign these values to your the corresponding elements in the system of relations, the system of relations is solvable, and at the internal vertices, it will provide the value of a KP function at the other double points. Okay, so you get a consistent construction, and you are able to reconstruct the divisor, the KP divisor.
Sorry.
For this reducible curve associated to this solution.
Simonetta, yeah?
Yes.
Oh, I have I don't know actually if there are questions from the audience on Zoom, but I have another short question or actually suggestion.
Okay.
So I mean, you have essentially, if you take a Krzyzewski construction, the tau function is a theta function on this M curve.
Yes.
Right? Now, and then when you degenerate the whole thing, you get the tau function of these line soliton, which is also a determinant.
Yes.
But so you didn't prove directly that the theta function converges to that determinant.
Sorry, I did miss the last part of the question. So
did you prove directly or indirectly? I guess it stands to reason that you proved indirectly that
it's indirectly, yes, yes.
It's not direct. It's not direct. Sorry, I missed it. Is it direct that you prove that the theta function becomes the determinant, or indirect?
No, it's indirect. I mean, it's indirect because what we do, we start from the Soliton solution.
Okay, I see. So because I may point out.
These are two red arrows, the horizontal from the Soliton solution.
Yes.
To the KP data, and then you desingularize the curve and you get the desingularized curve. So it's yeah.
Right. So then my question and suggestion is the following: to ask you to consider also partial degenerations.
Yes, of course. That would be very interesting.
There is a recent paper by some people. One is me, and the other is Alex and Bob Jenkins, where we show that if you, in general, if you take a Riemann surface and you perform partial degeneration, and you look at the theta function with the appropriate characteristics, it factorizes in the limit as a determinant of something, which looks exact of a Fredholm type matrix, identity plus something, and a theta function on the desingularization of the limiting curve. So what I think,
very interesting.
I think that you probably in our desingularization is chosen so that the limiting curve is connected. The nodal curve is connected. You need disconnected pieces, but I think the principle should stand also in that case.
No, well, my part, no, it's also, I mean, it's connected at the double points in my case.
Well, I mean, yes, okay, but it's what I meant that the desingularization. Well, yeah.
No, but the desingularization is.
Sorry, I meant to say that each smooth component. So there's only one smooth component with. Okay.
Yeah. Okay, I understand what you mean. Okay.
Anyway, but it's and also there is this chapter, probably you know, at the end of the second book of Mumford, Tata Lectures on Theta.
Yes.
You know that chapter, right? So it discusses the generalized Jacobian.
Yes.
And it shows how the theta function becomes some kind of determinant. So actually, that's where we got the idea, and then we cleaned up the story.
I understand. No, that's very important. You consider in a solution with complex times or real? I mean, the solutions.
That was just a pure theta function. There's an application to KDV, but it was pure theta function considering.
So it's in the complex setting, let's
say.
Yeah,
in complex setting, right? So you have to, of course, specialize to M curves and involution.
Because yes, it's somehow different the case of complex curves, because that is really Gelfand-Serganova, so it's a different story, much more complicated. So the fact, in a certain sense, the fact that you impose reality in the Postnikov construction provides you with some rigidity. Okay. No, if in the complex case, it's much more involved, what you cannot have, because you don't have anymore this strict condition of one divisor point in each oval. You understand? You could have something different.
I have a small question to both of you about this.
Okay.
As I remember, and I don't remember so well, but in order to get pure solitons, not something that others singularities or pure soliton solutions, and no quasi-periodicity, just solitons. What used to be done with, I don't know, hyperelliptic curves and various things, is pairwise degeneration. It's always two branch points that coalesce. In what you're doing, Simonetta, is it, and also Marco, is it when you say degenerate or the partial degenerate? The partial, do you mean always pairwise, or could there be more branch points that coalesce?
I think it's always pairwise because you only have nodal curves, I think, right, Simonetta?
Yes.
You have more than two, I guess you pick up holes and
if you have more than two, you get some kind of, well, it depends on cusps, right? So
you can have, of course, this is not the only possible degeneration that you can imagine. So that's, you can have wilder things, of course. Which provide you, for instance, with rational solutions, KP rational solutions, part of the degeneration.
So the Simonetta, thanks, but this conversation has spilled over significant. We kind of monopolized this the time, but
yeah, sorry for that.
I don't know if I hope that there are no, I hope now that there are no more questions, because otherwise we'll never go for lunch. So in that case, let's thank Simonetta.
Thank you very much.
Thank you.